Hey Bernard, how's it going?
Pretty swell, Sarah. I'm looking forward to a morning cup of joe.
Yeah, I think I'll get tea. Too bad nobody seems to work at this coffee shop.
Yeah, I wonder who left the door unlocked. It seems like we shouldn't have been able to come in.
Well, what should we do now that we're here?
Oh hey, have you heard about the interesting phenomenon of white dwarf pollution?
I have only heard a little about this, but I do know what a white dwarf is. Those are the hot, dense cores of stars after they have stopped burning fuel and have shed their atmospheres. White dwarfs are everywhere. They are the final stage of 97% of all stars.
Yep, and there are a lot of white dwarf stars that have heavy metals on their surfaces. That's white dwarf pollution. The way people discover polluted white dwarfs is with spectroscopy. If you see absorption features from heavy metals in the spectrum of a white dwarf, then you can conclude that there must be heavy metals on the surface of the white dwarf.
Sounds pretty boring. What's special about that?
Well, white dwarfs are really dense and have high surface gravity, so those metals shouldn't be sitting on the surface, they should have sunk deep below the atmosphere. It should only take on the order of 1 to 10 years for fresh metals to sink below the surface and no longer be observable.
Oh, so something must be constantly supplying material to the surface of the white dwarfs, so when material sinks below the surface, there's a new layer to replace it. I wonder what it is that supplies the material.
Exactly, me too. And I read a paper recently that offers an explanation for where this constant supply of material comes from. It's called Unstable Low-Mass Planetary Systems as Drivers of White Dwarf Pollution by Alexander J. Mustill et al.
What's their explanation? The only explanation that I've heard before is that these white dwarfs are feeding on the remnants of the planetary systems that they had as main sequence stars. This has even been supported observationally by the presence of debris disks around white dwarfs, and in one case, there have even been observed transits of disintegrating planetesimals. How could it ever get more exciting than that?
Oh, believe me, it can get so much more exciting. In these planetary systems, it is thought that there are two populations of objects, a reservoir of planetesimals and a small number of planets. Occasionally planetesimals scatter off of the planets and are thrown towards the white dwarf. These objects are shredded by tidal interactions with the white dwarf and rain heavy metals onto the surface of the white dwarf.
And that's the source of the heavy metals we see on polluted white dwarfs. Amazing. So these interactions must happen relatively frequently if white dwarfs are to be constantly polluted, right? If it only takes years for the metals to sink below the surface, then planetesimals must be thrown towards the white dwarf on year timescales as well.
Yep, and that was the major focus of the paper I read. What types of planetary systems can lead to a constant delivery of planetesimals to the white dwarf for long periods of time? To do this, they ran n-body simulations of systems with 3 planets and a belt of planetesimals. They varied the masses and spacings of these planets to see which lead to the most steady delivery of planetesimals for the longest period of time.
Well, I'd think that systems with more massive planets would be better at delivering planetesimals to the white dwarf. Just like how Jupiter has the biggest influence on asteroids in our own solar system.
That's what I thought at first too, but actually what this paper found is that systems with high-mass planets burned through their reservoirs of planetesimals too quickly and tended to eject more planetesimals from the system instead of scattering them into the central white dwarf. So they aren't likely candidates to explain all the systems with white dwarf pollution that we see.
Well, that's unexpected. Wait, if all these planets and planetesimals are on circular orbits, why would any of these interactions ever happen in the first place? Why would planetesimals get scattered in towards the white dwarf? Shouldn't every object in the system orbit happily for all eternity?
That's probably what the system was like when the white dwarf was a main sequence star, but things changed when it became a white dwarf. At the end of the red giant stage, the central star loses a lot of mass and that affects the orbits of its planets.
Oh, I see. And then planets can enter into eccentric orbits, and that's what allows them to cross paths with planetesimals and scatter them towards the white dwarf. But wait, if the planet paths cross too much, could the planets themselves be ejected from the system entirely? What would deliver mass to the white dwarf then?
This was addressed in the first set of simulations the authors of this paper ran. These simulations had only planets, no planetesimals, and they were run in order to see how stable the system was after the central star became a white dwarf, and what they found is that systems with low-mass planets are able to sustain instabilities for longer without loss of a planet than systems with high-mass planets.
Oh okay, so just from that aspect alone, low-mass systems seem to be a good explanation for systems with polluted white dwarfs, because they are able to withstand the instabilities necessary to shepherd planetesimals in towards the white dwarf for longer.
Exactly. Take a look at these plots from the paper. They show results from simulations that were ran with 3 planets and a belt of planetesimals. In particular, they illustrate how the accretion rate changes with time in systems with low mass, moderate mass, and high mass planets from the simulations they ran. Notice how high mass systems only have significant accretion for about 50 million years tops, whereas low mass systems can sustain accretion for multiple billions of years.
Okay, so most of the systems with polluted white dwarfs that we observe are going to be best explained as systems with low mass planets, because these are the systems that can sustain accretion for a long time. That's neat.
Yeah. And they were even able to show that their simulations of low-mass planetary systems were consistent with observed accretion rates of white dwarfs. Look at this plot showing how the accretion rates from their simulations compare to real observed accretion rates.
Oh my, what a sight! So their simulated accretion rate as a function of time lines up with observed accretion rates of white dwarfs at different cooling ages. Amazing.
Yeah, so it seems pretty clear now that all polluted white dwarfs we see have planetary systems with exactly 3 low-mass planets. Neat, right?
Whoa, I think you're getting ahead of yourself. They only ever ran simulations with 3 planets. So it's hard to tell anything about the likely number of planets in these systems from just their results.
Oh, good point. I wonder what results they would see for systems with different numbers of perturbing planets.
Yeah, but their results at least confirm that low-mass planets do a better job of delivering mass to the white dwarf at a steady rate than higher-mass planets do. So that's something. In the future, maybe they could run simulations with different numbers of planets to see if the number of planets plays a big role in how well mass is delivered to the white dwarf.
That would be cool. Well, this has been an interesting conversation. Too bad no coffee shop employees showed up to serve us coffee.
Yeah, that is too bad. Do you want to go look for coffee somewhere else?
Yeah, let's do that.